Welcome back to the deep dive. Today we are doing something a little different. We are time traveling.
Oh, okay. I'm intrigued.
I want you to close your eyes for a second. Just imagine it is November 2026.
Right around the corner.
It is. And you are sitting in the driver's seat of a prototype vehicle. You're on a test track in northern Sweden. It is cold.
How cold are we talking?
-7 degrees Celsius to be exact. The wind is just cutting right through the door seals.
That is a very specific and very chilly visual to start with.
It is specific for a reason.
Yep.
So you are staring at the engineering dashboard, but it's not showing you what you're used to. It's not just RPM and speed.
Okay.
You're seeing a live stream of brake dust particulate counts measured in milligrams per kilometer.
Wow. Real time.
Yeah, and you are seeing a real-time trust boundary verification code confirming that your emissions data hasn't been hacked by some third party.
The cybersecurity aspect.
And crucially, you are watching a countdown timer. You have exactly 10 seconds to get the catalytic converter from freezing cold to 400 degrees Celsius, or the car fails certification.
And that right there is the new reality of Euro 7. It is a completely different world from what we were dealing with in the Euro 6 era.
Totally.
It's no longer about just, tuning an engine. It's about managing a whole digital and physical ecosystem.
Exactly. And that is our mission for today. We aren't just talking about regulations, we are role-playing.
All right, I'm game.
For the next hour, I want you, our listener, to imagine you are a senior technical strategy consultant at a top-tier firm.
Mm-hmm.
Your client, a major automotive OEM, has just panicked. They realize that Euro 7 isn't just about the tailpipe anymore. It's about the entire digital and physical life cycle of the car.
And your job is to calm them down and give them a strategy, a McKinsey-style report.
Yes.
We need to be top-down, and we need to be IMI, mutually exclusive, collectively exhaustive.
I love when you get into consultant mode. MECE. Break it down for anyone who hasn't spent time in a boardroom recently.
It just means we aren't just throwing spaghetti at the wall. We're going to organize this chaos.
Okay.
We're taking this huge problem and breaking it down into distinct, non-overlapping pillars so that we can tackle each one methodically.
And we've got the source material for it.
We do. We have a massive stack of confidential reports here. I mean, deep technical data from AVL on lifecycle costs, detailed schematics from Garrett Motion on e-boosting, and some high-level industry strategy papers on the 2024-2026 window.
So the goal is to synthesize all of this into a coherent roadmap for our client.
That's the mission.
So what are our 3 pillars? How do we organize this mess?
Okay, so pillar 1 is the powertrain. Specifically, how do we solve the impossible physics of the cold start?
But the 10-second problem.
The 10-second problem. Pillar 2 is the vehicle and life cycle. This is the stuff that used to be invisible brake dust, tires, and the carbon footprint of actually making the car.
The cradle-to-grave stuff?
Precisely. And pillar 3 is the brain digital compliance and cybersecurity.
This is huge. It's no longer just does the tailpipe smoke.
Not at all.
Is the software secure?
Right.
And did the battery factory use green energy?
Precisely. The scope has exploded. We are looking at Regulation EU 22412557. This is the Bible for the next decade of automotive engineering.
Right.
And the stakes. If you don't get this right, you don't sell cars in Europe. It is that simple.
Okay, let's unpack this. Before we get into the nuts and bolts of the pillars, give us the top-down view. What is the strategic landscape looking like in this near-future scenario?
The headline is this. We are shifting from point-in-time certification to lifetime surveillance.
That sounds ominous. Surveillance.
Yeah.
Like Big Brother.
In a way, yes. I mean, under Euro 6, the previous standard, you built a prototype, you golden sample tuned it,
You got it just right for the test.
Exactly. You passed the test on a rolling road or a specific track, and you were largely done. You got your stamp. Euro 7 changes the game. It says, we don't trust your prototype. We want to know what the car is doing when it's 5 years old, with 100,000 kilometers on the clock, driven by a taxi driver in aggressive traffic in the winter.
So the car is telling on itself.
Essentially, it's the onboard monitoring, or OBM, we'll get into. But let's look at the timeline first, because that's what stresses everyone out.
Okay.
For light-duty vehicles, your standard passenger cars, the new type certification deadline is November 2026.
That is right around the corner in automotive development time. Usually, a car program takes 4 or 5 years.
Exactly, it's tomorrow. And for all registrations, meaning every single car sold, it's November 2027. So if you haven't frozen your hardware design by now, you are already late.
And this applies to everything, right? Not just gas guzzlers. I think there is a misconception that Euro 7 is just an engine rule.
That's a huge misconception. The regulation is built on the technical neutrality principle.
Meaning?
The regulators don't care if it's a diesel truck, a gasoline hybrid, or a battery electric vehicle. They all fall under the same umbrella.
Ah, okay.
Obviously, an EV doesn't have a tailpipe, so it doesn't worry about NOx. But it has heavy batteries, which means more tire wear, and it has brakes. And Euro 7 regulates all of that.
So if I'm the consultant, my first slide to the client is stop thinking about the engine test cell. Start thinking about the car's entire life.
Exactly. And that brings us right back to the MEC breakdown. We need to solve 3 problems simultaneously.
Oh.
1, the powertrain must be clean from the first second of ignition. 2, the vehicle itself must stop shedding microplastics and heavy metals. And 3, the digital twin must be secure and truthful.
Let's dive into pillar 1 then. Active thermal management, or, as I like to call it, how to heat a catalyst in 10 seconds without going broke.
This is where the physics gets really unfriendly. As we mentioned in the intro, the requirement covers a cold start at -7 degrees Celsius.
Which is freezing. That's a Nordic winter morning. My phone would die.
It is bone-chilling. Now, in the old days, you could rely on passive heating.
Right, just let the engine heat up normally.
Yeah, you start the engine, the exhaust gets hot, eventually that heat travels down the pipe, the metal heats up, and the catalytic converter starts working.
And how long does that take?
That takes maybe 60 to 90 seconds, maybe even 2 minutes in the real cold.
And under Euro 7.
You don't have 60 seconds, you have maybe 10. The regulation sets an emission budget for the first 10 kilometers.
An emission budget?
Yeah, think of it like a piggy bank. If you blow your whole budget in the first minute waiting for the catalyst to wake up, you fail the whole trip. Doesn't matter how clean the car is after that.
And there is a conflict here with the engine design itself, right? We've been making engines more efficient to meet CO2 targets, which actually makes this heating problem harder.
It's the Miller cycle paradox. It's a classic case of solving one problem and creating another.
Okay.
To get better fuel economy and lower CO2, almost all modern engines use the Miller cycle.
Can you explain that simply? What is the Miller cycle actually doing inside the cylinder?
Sure. So in a standard engine, the intake valve closes right when the piston starts moving up to compress the air. Simple enough.
Okay.
In a Miller cycle, you leave that intake valve open for just a fraction of a second while the piston is already moving up.
So it's pushing some of the air back out.
It pushes some air back out into the intake manifold. This reduces the compression work the engine has to do. It's great for efficiency. It's like getting a little push on a swing.
There's always a but.
But because you are expanding the gas more than you are compressing it, the exhaust gas comes out much cooler.
Ah.
You are extracting more energy as work, so there is less energy left as heat in the exhaust.
So the very thing that makes the engine efficient is starving the catalyst of the heat it needs to work.
Exactly. And it gets worse. Miller cycle engines also have poor transient response.
Meaning they're sluggish.
Yeah, when you step on the gas, it takes a moment to build power because you've optimized it for steady cruising, not for quick acceleration. So you have a cool exhaust that can't heat the catalyst and a sluggish engine. It's a disaster for emissions.
Enter Garrett Motion. I was reading through their technical deep dive, and they have this solution involving 48-volt systems. Why 48 volt? Why not the standard 12-volt battery we've had for decades?
The 12-volt system just doesn't have the muscle. It can't do the job.
What happens when you try?
Well, Garrett did a side-by-side comparison. They took a standard 1.5-liter TSI engine, a very common engine type used in millions of cars, and tried to solve this with a 12-volt secondary air pump.
Yeah.
It failed miserably. The 12-volt pump is weak. It can't control the airflow precisely. It makes the lambda, the air-fuel ratio, fluctuate wildly.
So it's sloppy.
Very floppy. And critically, when the engine is under high load, there's too much back pressure in the exhaust. The little 12V pump just can't push air in. It hits a wall.
So it works when you're idling, but the moment you drive away and put load on the engine, it stops working.
Precisely. And Euro 7 is all about real driving emissions. You aren't just idling, you're merging onto a highway.
Okay, so 12 volt is a non-starter.
Total non-starter. So Garrett brought in the 48V e-compressor. This thing is a beast. It spins at 90,000 RPM.
90,000, that is jet engine speed.
It effectively is a mini jet turbine. And because it's 48 volt and high speed, it doesn't care about engine speed. It's completely independent.
So it can just force air in whenever it wants.
It can force air into the exhaust even when the engine is screaming at high RPM. We're talking 6 kilowatts of power versus maybe 300 watts for the 12V system. It's It's a whole different league.
And this is the P2 layout they mentioned. What does that mean?
Right. P2 refers to its placement. They put the E-compressor after the intercooler, but before the engine intake.
Why there?
This is strategic. It allows the device to do two jobs. It can act as a booster for the engine to improve performance, which solves that sluggish Miller cycle problem we mentioned.
So it fixes the drivability.
It fixes the drivability, and it can also divert air to inject for emissions control. It's a 2-for-1 value prop for the OEM.
Let's talk about the chemistry, because this was the part that really blew my mind. They're essentially turning the exhaust system into a flamethrower to heat the catalyst.
Controlled combustion, please. We don't want flames shooting out the back.
Right. Controlled, but still.
But yes, it's fascinating. The strategy is to run the engine rich.
Rich means more fuel than air.
Correct. You deliberately inject extra fuel into the cylinder, so the exhaust gas coming out is full of unburnt hydrocarbons, essentially fuel vapor.
Which is normally a really bad thing for emissions.
Normally, yes, it's
Yeah.
terrible. But then the E-compressor injects a precise, high-speed blast of fresh, oxygen-rich air right before the catalyst.
So you have fuel vapor from the engine, you have oxygen from the E-compressor, and you have the hot surface of the catalyst.
Boom. You get an exothermic reaction right on the surface of the catalyst. It's like a little afterburner. The catalyst heats itself up from the inside out.
How fast are we talking? What did the data show?
The data from Garrett was staggering. They measured the catalyst temperature, what they called T1T, and it rose by 110 degrees Celsius in just 10 seconds.
That is incredible speed. That's like a flash fire.
It is. And the emissions drop is massive. NOx reduced by 61%, hydrocarbons reduced by 69%. This isn't a marginal gain. This is the difference between passing and failing the Euro 7 cold start.
And it does this without needing a massive, expensive electric heater that drains the battery.
Exactly. It uses the chemical energy of the fuel, which is already there, triggered by the electric air injection. It's much more efficient than trying to heat a huge chunk of ceramic with a battery coil.
It's the difference between using a lighter to start a fire versus trying to heat the wood with a hairdryer.
That's a great analogy. It's about triggering a reaction, not just brute forcing heat into the system.
So if I'm advising the client, the recommendation is clear. Passive heating is dead. 12V is dead. You need 48V e-boosting if you want to survive the cold start.
Correct. It's the only way to reconcile the efficiency of the Miller cycle with the heating requirements of Euro 7. It allows you to keep the engine efficient while keeping the catalyst happy. It solves the paradox.
Before we leave the powertrain, we have to touch on the heavy-duty side. The trucks. They have a different set of problems, don't they? A truck engine is massive compared to a 1.5-liter car engine.
They do. It's a different scale entirely.
Yeah.
Trucks don't just worry about the first 10 minutes. They worry about hauling 40 tons for 8 hours straight.
So what's their big thermal challenge?
Their problem is keeping the system hot during low load times, like when they are stuck in traffic or idling at a delivery dock or even just coasting down a long hill.
A massive diesel engine cools down that fast.
Surprisingly fast when it's idling. It's so efficient at idle that it doesn't produce much waste heat, so the after-treatment system can cool down and stop working effectively.
And the solution for that is the dual SCR strategy.
That's the industry standard now.
Yeah.
SCR stands for Selective Catalytic Reduction. That's the system that uses AdBlue or DEF to kill NOx. In Euro 7 trucks, you have two of them. One is close-coupled, bolted right to the engine manifold. It gets hot fast and handles the cold start and low-load city driving.
And the second one?
The second one is underfloor. It's further back in the chassis. It's bigger, and it handles the high-load cross-country highway driving when the exhaust flow is massive.
It's like a relay race. The first catalyst passes the baton to the second one as the conditions change.
Exactly. But Euro 7 throws a curveball at trucks. A new set of things to worry about.
Of course it does.
We now have to monitor new pollutants, ammonia, NH3, methane, CH4, and nitrous oxide, N2O.
Nitrous oxide. Laughing gas.
The very same. But it's no joke in the atmosphere. It's a potent greenhouse gas, about 300 times worse than CO2. And ammonia is what we use to clean up the autocox.
So wait, the cleaning agent itself is now a pollutant.
It is if you overdose it. It's called ammonia slip. You have to inject enough ammonia to kill the anox, but if you inject too much, it slips through the catalyst and you fail the ammonia slip test. It's a high-wire balancing act.
It sounds like an endless cycle of chemical management. You add a chemical to solve one problem, and then you need to monitor that new chemical.
That is the nature of emissions engineering. It's an asymptotic curve. We are chasing the last 1% of pollution, and the complexity required to get there is exponential.
Which brings us perfectly to the idea of unintended consequences. We solve one problem, we create another. That is the theme of Pillar 2, life cycle and non-exhaust emissions.
This is where the technical neutrality really bites. For 100 years, pollution meant exhaust. If you had an electric car, you were zero emission.
And Euro 7 says.
Euro 7 says not so fast.
Because cars wear out, they shed particles.
They do. Brake dust, PM10. Particulate matter, 10 micrometers or smaller. These are tiny particles that get lodged in your lungs. It's a serious health concern.
And Euro 7 puts a number on it.
A hard number, 7 milligrams per kilometer.
And this applies to EVs, too.
It applies to everyone. In fact, EVs can be heavy due to the battery, which puts stress on brakes.
But don't they use regenerative braking? They hardly use their physical brakes.
Yeah, they do, and that helps a lot.
Yeah.
But it also creates a very specific issue, the rusty disc syndrome.
Sounds like a medical condition.
It's an EV condition.
Yeah.
Because you use the electric motor to brake most of the time, that's the regenerative braking. The physical cast iron brake discs hardly ever get used.
So they just sit there.
They sit there and they get wet, they get salty in the winter, and they rust. Then when you finally do a panic brake, where the system periodically cleans the discs, that layer of rust grinds off and creates a massive spike in particulate emissions.
So the EV might actually emit more brake dust in that specific moment than a gas car.
In that single event, yes. It's a huge burst. So how do we fix that? We can't just tell people to brake more.
Right.
We use technology, laser cladding, specifically laser metal deposition, or LMD.
I saw this in the industry report. It sounds like sci-fi.
It's very cool manufacturing.
Yeah.
They take a standard cast iron brake disc, and they use a high-power laser to essentially weld a very thin, very hard coating onto the surface.
What's the coating made of?
Usually a nickel-based alloy, or sometimes tungsten carbide.
Yeah,
It's incredibly hard stuff.
Like coating it in armor.
Exactly. It makes the disc incredibly wear-resistant. The wear rate drops by 80%. The PM10 drops by 90%.
Wow.
And crucially, it doesn't rust. It stays shiny and clean even if you don't use it for a month. No more rusty disc syndrome.
So the strategic insight here is that the brake supplier ecosystem is about to get turned upside down. If you are casting cheap iron discs, you are in trouble. You need laser cladding capacity.
Or you need to partner with someone who has it. This is a supply chain bottleneck waiting to happen. The machines to do this are expensive and slow compared to just casting iron.
So if I were advising a tier 1 brake supplier right now...
I'd say buy lasers now.
And tires. That seems even harder to control. You can't coat a tire in tungsten.
No. And tires are becoming the #1 source of microplastics in the ocean. It's a huge environmental issue. Euro 7 is the first regulation in the world to demand limits on tire abrasion.
How do they even measure that? It feels impossible to track tiny bits of rubber flying off a tire on the highway.
It's really difficult.
Yeah.
They moved from the lab, from those big spinning drums, to the road.
Okay.
The official method is the convoy method. You have a convoy of identical cars driving thousands of kilometers on public roads, and they precisely weigh the tires before and after to measure exactly how many grams of rubber are lost per 1,000 kilometers.
So tire manufacturers are now in the emissions game.
Big time. They have to reformulate the rubber compounds to be more durable, but still have enough grip. It's a classic engineering trade-off.
Right. If you make the tire too hard to save emissions, it slides in the rain.
And if you make it too soft for grip, it fails the abrasion test. It's a very fine line to walk.
Let's talk about the biggest trade-off of all, the carbon footprint of making the car. We have this deep dive from AVL on design to CO2. This is where things get really counterintuitive.
This is my favorite part of the stack. It challenges everything we think we know about green engineering. It's fascinating.
Oh, the battery cover case study. Walk us through it. This is a perfect example for our listener to put in their report.
Okay, imagine the cover that goes over the massive battery pack in an EV. It needs to be strong, needs to be crash-proof, and it needs to be perfectly sealed.
Okay.
The instinct of every automotive engineer for the last 20 years has been make it lighter. Lighter means more range, better efficiency.
So you use aluminum or composite materials?
Right. SMC sheet molding compound. It's a fiberglass composite. Very light, very strong. It's the advanced solution. But AVL ran the numbers on the carbon cost of making it. The composite is terrible for the planet to manufacture. The energy required to make the glass fibers, refine the plastic resin, and then mold it under high heat and pressure is huge.
And recycling?
It's almost impossible to recycle effectively. You basically have to grind it up and use it as filler in something like concrete. The value is lost.
So what's the alternative?
Steel. Good old-fashioned steel.
But steel is heavy. If I put a heavy steel cover on my EV, don't I lose range? And if I lose range, don't I use more electricity from the grid over the car's life?
You do. It's absolutely true. But steel production has become very efficient, especially with recycled content. And steel is infinitely recyclable.
So you're trading weight for manufacturing footprint.
Exactly. And AVL's data showed that in certain energy mix scenarios, choosing the steel cover over the composite one saved 20% of the life cycle CO2 equivalent.
20%.
20%. Even accounting for the fact that the heavier car uses slightly more electricity to drive.
That is the aha moment. We are so obsessed with tailpipe efficiency, or in this case, range efficiency, that we forgot the manufacturing carbon costs.
Exactly. The carbon debt you create by making the composite part is so high that the car would have to drive for 300,000 kilometers just to pay it back in energy savings. Steel pays it back instantly.
This changes the bill of materials completely. Procurement isn't just asking how much does it cost, they're asking how much CO2 does it cost.
AVL calls it the dual metric bomb. Every single part has a price tag in euros and a price tag in CO2 grams, and you have to balance both. You might pay a little more in euros to save a lot in CO2, or vice versa.
It complicates the design process, though. Now an engineer has to be an environmental accountant.
That's the job description now.
Yeah.
And speaking of balancing, let's talk about the motor itself. The EDU electric drive unit. AVL had a strategy there too. Spin it faster.
How does spinning it faster help the planet?
It seems unrelated, right? But it's about material reduction.
Okay.
The tech is a high-speed PMSM permanent magnet synchronous motor. The logic is simple physics. Power equals torque times speed.
Right.
So if you want a certain amount of power, you can either have a big, heavy, high-torque motor that spins slowly, or you can have a small, light, high-speed motor.
And small is better for carbon.
Much better. A smaller motor uses less copper and fewer rare earth magnets. And those materials are incredibly carbon-intensive to mine, refine, and ship around the world.
So what kind of speeds are we talking about?
Going from, say, a standard 12,000 RPM motor up to 20,000 RPM, or even higher. By spinning it faster, you can shrink the motor, save 10% on the life cycle CO2, and actually improve the system efficiency by 25%.
But spinning faster brings new problems, right? I'm thinking noise, vibration, bearings exploding.
Oh, absolutely. The NVH noise, vibration, dryness becomes a nightmare. You get this high-pitched mosquito whine that drives people crazy. And the bearings need to be ceramic or specialized steel to handle the heat and the speed.
So it's another trade-off.
It is, but that's a solvable engineering problem.
Yeah.
The carbon savings from using fewer critical minerals are worth it.
One last point on the life cycle from the AVL report. Location, location, location.
The energy mix. This
Yeah.
is critical. Where you build your battery matters as much, if not more, than the specific chemistry inside it.
Really? More than NMC 811 versus 622.
Yes. Building a battery in a country that burns a lot of coal-like, historically parts of Eastern Europe or Asia, creates a massive carbon backpack for that component. Building the exact same battery in Sweden, using their hydro and wind power, cuts the manufacturing carbon footprint in half.
So we are going to see a strategic relocation of the supply chain.
We already are. People call it green shoring. Factories are moving to where the green electrons are. If you are the consultant, you need to tell your client, don't just look for cheap labor, look for clean power.
Okay, so we've built a clean powertrain and we've designed a low-carbon car. Now we have to make sure it stays compliant. Pillar 3, digital compliance and security. The brain.
This is where the consultant needs to sit down with the IT department, the software guys, the hackers. Because Euro 7 introduces OBM onboard monitoring.
How is this different from OBD onboard diagnostics? We've had that since the 90s. My old car has a check engine light.
It's a fundamental difference in philosophy.
Right.
OBM is about finding faults. Hey, a sensor's broken, turn on the light. It was binary, broken or not broken.
Got it.
OBM is about measuring reality. It's not a Boolean check. It's quantitative. It's constantly asking, hey, you are emitting 85 milligrams of nutcox per second.
It's measuring the actual mass flow of pollutants.
Correct. It has to calculate mass flow in milligrams per second and then integrate that over the entire trip. It's performing calculus in real time. It's not just looking for a broken wire. It's auditing the exhaust gas minute by minute.
And this data, where does it go? Does it get beamed up to Brussels?
Not automatically, no. It stays on the car, but it's available to the authorities during inspections. And this creates a massive incentive for cheating.
Cheating. You mean like aftermarket tuning?
Exactly. I mean, imagine you are a truck driver. You can save 5% on fuel if you turn off the AdBlue injection. Or you are a sports car enthusiast and you want more power, so you delete the particulate filter software.
Or maybe you just want to sell a used car and you want to wipe the dirty history of high emissions trips?
All of the above. The temptation is huge. So Euro 7 requires the car to defend itself.
This is the trust boundary.
It is.
Yeah.
The regulation specifically references UN R155, which is the Automotive Cybersecurity Standard. We need a 3-layer defense model. It's like a fortress.
Okay, walk us through the layers. Imagine I'm a hacker. I want to spoof the NOx sensor to say the air is clean when it's actually dirty. How do you stop me?
All right. So your first move might be to try and rewrite the engine software, right? To just tell it to ignore the sensor.
Yeah, flash the ECU.
But later one stops you. That's the HSM hardware security module. This is a special hardened chip inside the ECU that stores the cryptographic keys. It ensures secure boot.
What does that mean?
When you turn the car on, the HSM chip checks the software code against a known good digital signature. If a single line of code has been changed by a hacker, the signature won't match and the car will refuse to start. Or it'll go into a safe mode.
Brutal. So I can't rewrite the code. What if I attack the sensor itself, the hardware? Layer 2.
Layer 2 is authenticated communications. The NUCA sensor isn't just a dumb sensor anymore. It's a smart device with its own chip inside.
Okay.
When it sends data to the main computer, it encrypts it. It digitally signs the message. This prevents a man-in-the-middle attack.
So I can't just unplug the real sensor and plug in my own little black box that sends fake, clean signals.
You can try, but the main computer, the ECU, will say, "I don't recognize your digital signature. You are an imposter." And it will immediately flag a tampering incident.
Okay, very clever. So I can't change the software. I can't fake the hardware. What's left? What's layer 3?
Layer 3 is behavioral detection. This is where AI comes in. The car knows physics.
How so?
It knows that if you are at full throttle climbing a steep hill and the engine is consuming 20 liters of fuel per minute, you should be producing emissions. It's a physical certainty.
Right.
If the authenticated digitally signed sensor reports 0 emissions while the engine is under maximum load, the AI in the ECU says that is physically impossible.
I'm being lied to.
Exactly. And it flags it. Plausibility check failed. So even if you somehow defeat the first 2 layers, the car's own model of reality will catch you.
The report also mentioned something about hashing data at engine shutoff. Why the rush? Why within 10 seconds?
This is to prevent retroactive tampering. It's a clever bit of data security.
Okay.
The regulation requires that within 10 seconds of the engine turning off, the OBM system must take all the emissions data from that trip, run it through a cryptographic hashing algorithm like SHA-256, and store that hash.
It seals the record.
It seals the digital envelope. A hash is a unique fingerprint of the data. If you try to go back later with a laptop and scrub the data to hide a violation, the hash won't match the altered data anymore. It's proof of tampering.
It's like blockchain for your tailpipe.
That's a perfect way to put it.
This sounds incredibly complex to calibrate. How do engineers test all of this? We talked about noon to 7 degrees, 1,800 meters altitude, different driving styles. The matrix of possibilities is infinite.
It is infinite, and that is why physical testing is dead.
That's a bold statement.
Well, not completely dead, but
Yeah.
it's for validation only, not for calibration. You cannot calibrate a Euro 7 car on a track.
Yeah.
There isn't enough time in the universe to drive every combination of temperature, altitude, road grade, and traffic. You'd go bankrupt trying.
So we use digital twins.
We have to. Virtual calibration. You build a high-fidelity digital twin of the engine, the after-treatment system, the battery, the whole vehicle. Then you run virtual RDE scanning.
RDE being real driving emissions.
Right. You simulate millions of kilometers of driving in the cloud. You throw every possible condition at the digital model.
You find the failure points in the matrix before you even build a physical car.
Precisely. You find that one specific corner case, driving up a mountain in Spain at 35 degrees with a full load and a trailer, where the ammonia slip spikes for 3 seconds. And you fix the control software before a physical prototype ever exists.
This is a fundamental shift in the workflow of an automotive engineer.
It is. The test driver in a freezing car is now a simulation engineer managing a server farm. The proving ground is now Amazon Web Services.
Okay, we have unpacked the 3 pillars: thermal, life cycle, digital. Now let's put our partner hats on. We need to synthesize this into a strategic report. What is the global context? How does this stack up against the rest of the world?
It's a fascinating geopolitical chessboard. You have Euro 7, which is, as we've discussed, very monitoring focused. It's about surveillance and lifetime durability. Then you have China 7.
Is China 7 stricter?
In some ways, yes. But its focus is different. China 7 is obsessed with low NOx. They are pushing the absolute chemical limit of how clean the exhaust can be, but they are less concerned with the OBM surveillance and cybersecurity aspect than Europe is.
In the U.S., what's the EPA focused on?
The U.S. EPA is all about durability. They want the emission system to last for 15 years or 150,000 miles, guaranteed. They are less concerned with the minute-by-minute surveillance, but they want robust hardware that just doesn't break.
So Europe is positioning itself as the smart regulator.
The smart, and some would say the protectionist regulator.
How so?
There is a made-in-Europe strategic defense angle here. By enforcing these strict life cycle CO2 scores, remember the battery cover example, Europe is making it very hard for cheap imports from regions with dirty energy grids to compete.
Because if you make your car in a factory powered by dirty coal and ship it halfway around the world, your life cycle CO2 score will be terrible, and you might face tariffs or penalties.
Exactly.
Yeah.
It's protectionism disguised as environmentalism. It forces global manufacturers to set up clean factories inside Europe if they want to compete on a level playing field.
Clever. So let's get to the so what. What are our actionable recommendations for the client? Give me the top 4 bullet points for the executive summary of our report.
Okay. Recommendation 1. Adopt 48V e-boosting immediately. Stop trying to make 12V work for after-treatment heating. It's a dead end. If you want to solve the Miller cycle versus cold start trade-off, you need the e-compressor.
Yep.
Full stop.
Done. Recommendation 2.
Implement the dual metric bell. Your procurement team needs to fundamentally change how they buy parts. You need to list price and CO2e side by side on every component. Stop blindly chasing lightweighting if the manufacturing carbon debt is too high. Steel might be your new best friend.
I can see the procurement guys sweating already. Okay, recommendation 3.
Merge engineering and cyber. You can no longer have a powertrain team and a software security team in different buildings and different silos. The OBM is a security device. You need cyber physical teams. The person calibrating the on-ox sensor needs to sit next to the person running the encryption keys.
Breaking down silos, classic consultant move. I like it. And number 4.
Virtualize or die. If you are still planning to calibrate Euro 7 on the road with fleets of prototypes, you will miss the deadline and you will go over budget. You need to invest heavily in digital twins and virtual RDE scanning. Physical testing is for the final stamp of approval, not for development.
That is a solid roadmap. It's daunting, but it's clear.
It transforms the automotive engineer from a mechanic into a systems architect. You're not just building an engine, you're building a compliant, secure, low-carbon system.
Which leads us to our final provocative thought, the thing to leave the client thinking about.
We usually think of a car as a product. You buy it, you own it, it's yours. But under Euro 7, the car is more like an environmental asset that reports to the government.
It's a snitch. The car is a snitch.
In a way. But think about the implications. If your battery health drops below a certain threshold, reducing its efficiency, or your sensor data looks suspicious, the car itself might report you or restrict performance.
So your compliance isn't a one-time stamp at the factory.
It's a living, breathing digital state. It's a compliance score that fluctuates every time you drive.
Wow.
And that completely changes the relationship between the driver, the manufacturer, and the state. The engineer's job has now shifted from building engines to managing these environmental assets for the entire lifetime of the vehicle.
A brave new world indeed. Thank you. This has been an incredible deep dive into the maze of Euro 7.
Always a pleasure to unpack the complexity.
And to you, our listener, the senior consultant, good luck with that client report. You have the data, you have the MECE framework. Now go save the strategy.
Yeah.
Thanks for listening to this deep dive. We'll see you next time.